This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is DC current sources. Our objective is to introduce DC current sources and learn how to analyze circuits incorporating DC current sources. Let me begin this lecture by stating that there is no such thing as a current source. There are, however, variable voltage sources that increase or decrease output voltage in order to keep current at some preset constant value. This is a real-world current source. We'll return to this definition in a moment after I introduce the ideal entity known as a current source. This is the schematic symbol for a current source. It is a two-terminal device and induces conventional current through a circuit in the direction indicated by the arrow. This is a mathematically perfect entity and not necessarily constrained by reality. In theory, a 2 amp current source should push 2 amps through a 20 ohm resistor just as easily as it would push 2 amps through a 20 mega ohm resistor. But the real world says differently. We'll discuss limitations of real-world current sources in a moment, but for now, we'll just assume the current source behaves exactly like it's supposed to. Regardless of the applied load, a current source pushes the required amount of current through a circuit in the indicated direction, in this case, 2 amps. You'll be happy to know if you keep current sources at this level of abstraction, circuit analysis is exceptionally easy. If our load resistor has a value of 20 ohms, an application of Ohm's law demonstrates that the resistor will experience a 40-volt drop, implying that the current source must induce a 40-volt rise to allow 2 amps of current to travel through this 20 ohm resistor. If, however, the load is dramatically increased to 20 mega ohms, another application of Ohm's law demonstrates that the resistor would experience a 40 megavolt drop, which implies that the current source must induce a 40 megavolt rise to allow 2 amps to travel through a 20 mega ohm resistor. 40 megavolts. Can you see the difficulty in purchasing a current source that will push 2 amps through a circuit regardless of applied load? Not going to happen. However, if we suspend our disbelief in physics, sure, it could happen, and an Ohm's law analysis gives us the necessary proof it could. The current divider rule is an especially handy technique when performing circuit analysis using current sources. For reasons I'll explain in later lectures, current sources are often placed in parallel with a large fixed resistor and a variable load resistor. This is a perfect setup for the current divider rule. Incoming current is known, as are the resistor values. Consider a 29 mA current source supplying current to a parallel combination of a fixed 4.7 kilo ohm resistor and a variable load resistor presently set to 240 ohms. If you're up to the challenge, see if you can use the current divider rule to solve for the current through each element. Once you've got this information, see if you can solve for the voltage drop across each element. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The DC current divider rule set up to solve for the current through the fixed resistor is equal to the resistance of the element not of interest, in this case, the variable load resistor, divided by the summation of these resistances, fixed plus load, times the incoming current, in this case 29 milliamperes. Substituting our given values yields current through the fixed resistor to be 1.4 milliamperes. We could use another application of the DC current divider rule to solve for the current through the load resistor. However, I suggest a far more efficient means of doing so, namely Kirchhoff's current law. Given 29 milliamperes of incoming current enters this parallel relationship, and 1.4 milliamperes is diverted through the fixed resistor, an algebraic rearrangement of the Kirchhoff's current law equation for this parallel relationship suggests that current through the load resistor equals incoming current minus current through the fixed resistor. Substituting in our given values yields current through the load resistor to be the remaining 27.6 milliamperes of current. As a means of checking our work, an application of Ohm's law demonstrates the current source must produce a 6.6 volt rise. Voltage across these parallel elements is indeed the same, and what comes in does indeed come out. Let's say the variable load resistor now changes to 690 ohms. See if you can use similar techniques to solve for the current through each element and the voltage drop across each element. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Presented without comment, you should have found 3.7 milliamperes travels through the fixed resistor, and the remaining 25.3 milliamperes travels through the load resistor. An application of Ohm's law demonstrates that the current source must induce an increased 17.4 volt rise. Is it just me, or does circuit analysis with current sources seem suspiciously easy? Do you suspect a trap? Chill out. Relax for once. I know I've hammered you with some detailed lectures before, but this is the one occasion where it really is this simple. If you've got a solid understanding of Ohm's law and can make use of the current divider rule shortcut, analysis incorporating current sources really is this easy. Keep in mind, ideal current sources aren't exclusively limited to just pure parallel circuits. They could be included in basic series circuits or more advanced series parallel circuits. Consider this example of an 18 mA current source placed in series with R1, a 620 ohm resistor, R2, a 240 ohm resistor, and R3, a 470 ohm resistor. This is a totally different circuit than our previous parallel circuits, but well within the reach of those individuals with an understanding of basic series circuit properties and Ohm's law. The most fundamental property of series circuits is that current through elements in series is the same. The current source, being the only active source in our circuit, must therefore induce 18 milliamperes of current through the whole circuit. Source current equals I1, which equals I2, which equals I3, and they all equal 18 milliamperes. See if you can use series circuit properties to solve for the voltage drop across each element, and consider the necessary rise that must be present to induce these voltage drops. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Ohm's law states the voltage drop across an element is equal to the current through it times resistance. V1 equals I1 times R1, which yields 24.8 volts. V2 equals I2 times R2, which yields 4.3 volts. And finally, V3 equals I3 times R3, which yields 8.5 volts. Using Kirchhoff's voltage law, it can be said that the sum of voltage drops equals the rise induced by the current source. Substituting our calculated values, we find that the current source must have induced a 37.6 voltage rise to induce 18 milliamperes of current to travel through this series combination of resistors. See, it really is that easy. And that's the point. A current source is a mathematically pure entity and allows us to make these simplifications. If the circuit you're analyzing includes a current source, you can either whip out Ohm's law or the current divider rule, and the most complicated scenarios will fold just like an origami ballerina. We'll learn in later lectures that one can swap out certain configurations of voltage sources for an equivalent configuration of a current source and make the analysis easier, and the circuit will be none the wiser to the substitution. Additionally, we'll learn in much later lectures that various configurations of power electronics devices, known as transistors, can sometimes be modeled as current sources. For today's lecture, it's just a quick introduction to this entity.